3.2 Centripetal Acceleration. The hammer throw is a track and field event in which an athlete throws a hammer, a heavy metal ball attached to a wire and a handle, to the farthest distance possible. To do this, the athlete first swings the ball in a circular path. After giving it a maximum circular speed with 3 or 4 turns, the athlete releases the hammer, which then flies down the field. Just before the hammer is released, it has uniform circular motion, which is motion in a circular path at a constant speed. Uniform circular motion is the motion of an object with constant speed around a circular path of constant radius. By moving the ball in a circle, the athlete introduces the force of tension in the wire. This tension keeps the ball in a circular path. The greater the tension, the greater the acceleration towards the center of the circle, and the faster the ball moves in a circular path. When the tension is very large, so is the speed of the ball. When the athlete releases the hammer, the ball travels far down the field. Centripetal acceleration is the instantaneous acceleration that is directed towards the center of the circular path. With centripetal acceleration, the acceleration is always directed towards the center of the path. And let's examine why this happens. Though the object is traveling in a uniform circular path, it is changing direction. And the fact that it is changing direction is due to the tension in the rope. Otherwise, the object would want to continue in its path at that particular instant in a straight line. So in this case, acceleration is not in the direction that the object is moving, but is responsible for changing the direction of the velocity of the object. Let's examine the direction of the acceleration, the centripetal acceleration. Here we have initial velocity, v1, I'll label it v1, and we have final velocity, v2, I'll label it v2. We know that acceleration in general is equal to the change in velocity over time. So whatever the direction of this change in velocity is the direction of the acceleration. If we examine these two vectors and we find the change in v1 to v2, we can solve this in 2 different ways. First, I want you to look at the tail-to-tail method that we discussed in Chapter 2 for subtracting vectors. That is the line that joins the tip of v1 to the tip of v2, and notice they are tail to tail when we are subtracting vectors, so delta v is in this direction. And we can see that this direction is straight towards the center of the circular path. Now, another way to look at it is to have v2 minus v1. Here we have v1 in this direction, but minus v1 would mean that we are changing the direction of v1, flipping its direction. Just stylize that in green. So v2 minus v1 would look like this. This is the tail to tip method, in which we are adding v2 plus minus v1. And we'll see that the answer, delta V, is the line that joins the tail of the first to the tip of the last. In both of these examples, we can see that the acceleration is in the direction of delta V, and both of these delta V's are pointing towards the center of the circle. All right. Let's examine the equations for centripetal acceleration. As this ball travels around this entire circle, the speed of this ball or object can be calculated using distance over time. In for distance, we will put the distance traveled in one complete circular path, which is the circumference of the circle. Circumference can be found by the equation 2 pi r. And the time it takes to complete one complete path is known as the period, capital T. So we have an equation that states acceleration is equal to v squared over the radius we know that v is 2 pi r over period squared divided by the radius. If we simplify this, we have 4 pi squared r squared over t squared over r. If we simplify this, this becomes 4 pi squared r squared over t squared r. And we can simplify, we have an r on the bottom and r squared on top. We are then left with acceleration equals 4 pi squared r over t squared. So remember, period is the time required for a rotating, revolving, or vibrating object to complete one cycle. And frequency is the number of rotations, revolutions, or vibrations of an object per unit of time. It's the inverse of period. So we know that frequency is 1 over t. So if we have acceleration equals centripetal acceleration equals 4 pi squared r over t squared. Since 1 over t squared is equal to f, 1 over t squared equals f squared. Remembering that f equals 1 over t, so 1 over t squared equals f squared. We can then rewrite the equation for centripetal acceleration as 4 pi r f squared. Let's start by taking a look at an example. Sample problem number 1. A child rides a carousel with a radius of 5.1 meters that rotates at a constant speed of 2.2 meters per second. Calculate the magnitude of the centripetal acceleration of the child. Let's write down everything that's given in this question. We have a radius of 5.1 meters and a constant circular speed of 2.2 meters per second. And we want to find the magnitude of the centripetal acceleration of the child. Centripetal acceleration equals 4 pi squared r f squared. If we sub these values in, actually I'm going to go back a bit and use our original equation, v squared over r. We have 2.2 meters per second squared divided by a radius of 5.1 meters. If we punch this into our calculator, we end up with an acceleration of 0.95 meters per second squared. So remember, we have two equations for centripetal acceleration. The first one looks like this. And the second one looks like this. Both of these can be used to find centripetal acceleration. All right, let's take a look at sample problem number 2, calculating the magnitude and direction of centripetal acceleration. A salad spinner with a radius of 9.5 centimeters rotates clockwise with a frequency of 12 hertz. At a given instant, the lettuce spinner moves in the westward direction. Determine the magnitude and the direction of the centripetal acceleration. So, since the velocity is changing as the salad spinner rotates in a uniform circular path, we saw up above that this change in velocity will result in acceleration that is directed towards the center of the circle. Centripetal acceleration is always directed towards the center of the circular path. In this example, we are given a radius of 9.7 centimeters and a frequency of 12 hertz. We're going to use centripetal acceleration equals 4 pi r squared. Sorry, that's 4 pi squared r f squared. 4 times pi squared times 0.097 meters, converting this centimeters into meters, times the frequency 12 hertz squared. We end up with an acceleration of 5.5 times 10 to the power of 2 meters per second squared. Therefore, the centripetal acceleration at the moment shown is 5.5 times 10 to the power of 2 meters per second squared north. Let's look at sample problem number 3, in which we're calculating the frequency and period of rotation for a spinning object. The centripetal acceleration at the end of an electric fan blade has a magnitude of 1.75 times 10 to the power of 3 meters per second squared. The distance between the tip of the fan blade and the center is 12 centimeters. Calculate the frequency and the period of rotation of the fan. So we have the distance from the center to the tip of the fan blade, which is the radius, and is 12 centimeters, which is 0.12 meters. We have the centripetal acceleration, which is 1.75 times 10 to the power of 3 meters per second squared. And we want to find the frequency. We know that centripetal acceleration is equal to 4 pi squared r f squared. If we rearrange this, f is equal to the square root of centripetal acceleration over 4 pi squared r. Let's sub in our values. We have 1.75 times 10 to the power of 3 meters per second squared divided by 4 pi squared, 0.12 meters. Take the square root of this whole expression, and we end up with a frequency of 19.2 hertz. So if frequency equals 19.2 hertz, and period equals 1 over frequency, then we can find the period as 1 divided by 19.2 hertz, and we end up with 5.2 times 10 to the power of negative 2 seconds. So the frequency of the fan to 2 significant digits is 19 hertz, and the period of rotation is 5.2 times 10 to the power of negative 2 seconds. Try a few of the homework questions. See how you do. Good luck.